Although is my webcam thing getting picked up anywhere? I don't think so.
Well, I think you'll have to connect it to my laptop. Pick it up. Or we could ask him to turn on his webcam if he has one. Let's start in 2 minutes. Or could we go there?
2 minutes. It's like it's right after lunch, so yeah, 2 minutes.
I think we could start then. Right.
All right. Hi, everyone.
Well,
Can we give you an introduction? Thank you.
Hello everyone. It's my privilege to introduce Ben Birchfield, who's going to give our next keynote talk. Ben is a senior manager in the Large Behavior Model Division at TRI, Toyota Research Institute. He leads the multimodal policy learning and data teams, which are dedicated to creating state-of-the-art, general-purpose robots using foundation models trained at scale. Dr. Birchfield's work spans AI, machine learning, robotics, and computer vision. And he earned his PhD in CS from Duke University, after which he did a postdoc at Brown University. So, Ben, please take it away.
Awesome. So, I guess I'll dive right into it. I'm not really a rational learning person. My friends might say I'm not really a rational person, but I've given it my best attempt here. So, my background really is on foundation models for robots, in particular, with, I guess, what we call visual labor or pixels to actions types of approaches. So this is diffusion policy, and then more recently we've been doing a lot of work on scaling this up with sort of large pre-training runs in order to try to build more general purpose robots. And today I'm going to talk a little bit about what our robots should actually be rational about. So, at its core, what we have these policies that take in observations, they produce actions, and they train on a lot of data. And there's a whole life cycle that's involved in doing these things. So there's the data portion of that life cycle, evaluation portion of that life cycle, training portion of that life cycle. And each of these phases has different costs, and each of these phases has different ways that we can think about resource rationality. it's just a little bit of a background. So I'm going to talk a lot about what we call like behavior models here. And you can think of these as legal labor foundation models that are a generalization of single task behavior coding. So for those of you familiar with things like diffusion policy or ROHA, these would be single task policies that usually take in things like the camera images from your robot, potentially joint angles, what we call proprioception. And then they spit out actions, usually somewhere between 10 and 100 hertz. And these are things like either commanded joint angles or potentially manufacturing position and velocity. So the large versions of these are not multitask. They generate the language conditioning. So in addition to the robot's observations, they also get something like a prompt. Could be pick up a cup, a magnetic, clean the house, that sort of thing. And they now are trained on much more data. So generally, we combine data from many different robots as well as action-free data in the form of video and language data sets. So for a lot of what I'm going to talk about, this is the kind of architecture that we use. This is actually a PLA version of this. We also have a simpler one that uses a smaller pivot grid. But at its core, you have something that looks a lot like a VLM as a macro. So that's a multimodal model that consumes your text and images. And then there's a diffusion head as well, which is conditioned on the output from that module and actually is responsible for predicting the actions sent to the robot. We won't go too much into the details, but if folks have questions, please ask. So this is the sort of thing that you can do. So this is one of our policies that we train every summer. This was actually not a lot of data for this specific example. This was 500 demonstrations, so a few dozen hours of data. You can see they're somewhat perfect. One of the cool things about these sorts of behaviors, though, is that they tend to be naturally very close. So you get this sort of recovery without actually having to program a specific recovery demonstration. It also can be quite dexterous, although for steps that are public failure, helps a lot of the demonstrators in what they're doing. We tend to be pretty careful to show not only optimal demonstration, but also slightly suboptimal demonstration. So for some of the volume actually things that do really well, the robot has a little bit of data showing on that place. The other thing to note is that in this case actually it is not a force-aware policy. I like the end of this one here because you can actually see how much the robot can achieve the visual cues that infer force in the way. So it's tightening the back here. It uses cues like the thing settling down onto the bolt, understand what the position is, and then as the thing is actually floating down, it's going to use cues like the pitch and motion. In order to balance it. And I should add that these things are very much not perfect. This particular behavior, that works 10 times, most of the time it gives you a sort of large fraction pool for when instead of something that would be a computer program, you can do this with a couple dozen hours of data and exactly the same code that you use for teaching units. And so we spent a lot of time with this same sort of recipe suite. So, figuring out when you push through a different task, these sorts of long horizon behaviors, figuring out when we use things that are necessary. Highly one way in terms of the efficiency, so when you're cutting objects or you're permanently breaking things, you can't go back. So there's certain types of recoveries here that's not possible. And we found a few things, but one of the most critical ones is really the data quality here is incredibly good. So the biggest factor that separates our ability to do some of these things from, let's say, failure attempts is just the care that we put into curating that data and then sort of making curriculum for the robot. We want just the right amount of noise in the data set so that the behavior is brittle, but not so much noise that you corrupt the solution itself. I'll skip ahead a little bit here, but just to show one more thing that's kind of cool is you can actually deal pretty well with some high precision transitions, but the hard thing actually is that these policies are coming about something different. So you look at basically everything you do in a visual task progression, and even the difference between when you're sort of down slicing or you're halfway through, you can convert that color. So, and that's one of the big implications that you really work on these days. So, in a nutshell, that's the kind of behavior that I'm going to talk about today when I talk about rationality. And thinking about what is important to us and how we go about getting these things to work, there's kind of three, I would say, types of cost sensitivity that come to mind. So I'll talk about three types of rationality, three sorts of situations where we might think about rationality. So one is rationality with respect to a post-training data. That's the first one I'm going to talk about. The second is evaluation rationality. And then the third is actually rationality with respect to all of the evaluation. So the first thing we need to call out here is that actually we found that big models commonly are efficient. And I know one of the topics that's come up a few times here today is actually what does rationality mean in this era of big models? Does it even make sense to think about? And I would say yes, and actually for some of the things that we're sensitive to, a big model either are necessary to produce rationality. So what I mean by that is if you take 3,000 hours of data, so in our case we have 1,700 hours of pre-training data. This is a mixture of several hundred hours of our internal data with open source robot data, LXC, Droid, that sort of thing. And you do a big pre-training model, and you do a multi-task language condition model. And you take that model and you fine-tune it into a specialist. So now you're not learning from scratch, you're starting with some past experience. You found a really consistent state of laws in the behaviors that we analyzed. So we did 50,000 rollouts in simulation. This is actually kind of an understatement. This just is what we sort of talked about publicly because it was our cleanest and well-controlled experiments. But we found all the signal pointing in the same direction across hundreds of thousands of rollouts just in the last 6 months. Ended up in these 1,800 real-world rollouts. I think we probably done more than 5,000 or 6,000 of experiment rollouts in this regime as well. These are just the ones that are most carefully controlled. And really consistently what we see is that as we pre-train on more data, the amount of fine-tuning data, the amount of post-training data that we need for a specific level of performance increases. And that's actually really important because a lot of the effort that goes into getting these behaviors to work is actually that careful data curation and that careful teaching. It's super non-trivial still in order to understand exactly how do I demonstrate a thing and good results. And so even though there are costs associated with large-scale training, and even though you need to have all of that data in the first place, once you have it, once you have these big models, that's a one-time cost. And so you can use those to do many new things. And you're reducing a lot of the very expensive work that's required. And actually, one of the cool parts of the result is those behaviors that I showed earlier, those long horizon, fairly complicated ones, those aren't in the pre-training mixture. In fact, there's nothing like them in the pre-training mixture. We don't have anything super long horizon, no cutting, nothing complex like that. And so we're seeing, at least at this scale, some benefits, even when you're doing something that is in some ways outside of the scope of the pre-training distribution. And like I said, so here's a little bit of a look at just that exact data mixture. And it's a decent amount of data, but it's not quite a huge amount. And so you actually, you start to get a payoff pretty quickly. And as we found with the increase in quick speed. Here's a more sort of extreme qualitative example of what all of this effort in pre-training gets you. So these are exactly the same demonstrations of this particular task. It's a couple hundred examples. On the left is a model with 3,000 hours of pre-training data, and on the right is your track. There's a few things that we've noticed pretty consistently here. So obviously the pre-training one works better, so we showed that in the last part. But the way that it works better is really interesting. So these models with pre-training, the motions tend to be a lot smoother. So it's relatively better to buy or there's a reasonable motion per second. And it tends to be much faster to recover. So one of the very important ways when you do it from scratch is that you miss a step and you make a mistake and nobody's going to keep going. We call it airballing sometimes. It's like you miss the grasp and now you're moving through the air, so you're holding something that you're not. And we end up being just in general a lot more reactive with pre-training. You can get things to work from scratch, but it takes more data, and often at a bigger amount of data, the results are like the difference between something that most of the time works pretty decently well, and just clearly this isn't an easy thing to do. I'll cut it off here, but there's some funny examples. For this particular one, the difference is pretty stark. We take this and talk about this after other scenarios. All right. So that's one piece of rationality, and it's probably the one that I think most. I think that the longest reasoning makes sense. I actually argue that doing things from scratch is fundamentally irrational. People don't agree this way. You will never want to have to teach, let's say that you probably would talk to them, you never want to have to teach a person how the universe works from first principles. It's really nice to boost around lots of fundamentals. And that's the way I would think of it. There's another facet of rationality I think is often underappreciated, and that is just how much effort goes into evaluation. And actually, careful evaluation and thinking about evaluation properly is reasonably rational from the perspective of human effort, which more than robot hours right now, I think is actually a limiting factor. The scale of robot fleet is the people supervising it. So this is just to kind of illustrate why this is a problem. So this is a super simple plot of how the person confidence interval as a function of sample size. So basically what this is telling you is that depending on the true success rate of whatever you're measuring, if you have a certain sample size of robot rollout, here is the resolution with which you can determine what your success rate might be, right? The stochastic sample that you're estimating what that true success rate might be. So if you have something like n of 10 or n of 20, depending on the true underlying success rate, 0.3, 0.4, 0.5, that's kind of your 95% confidence interval. So if you made a change and you would be really excited if you made the robot 15% better, you're not going to rely on the detect that with sample sizes like this. And so, we turn it up a bit, and we did, and it's just, it takes effort, and it's expensive, and it takes you time. But you can pull these down a little bit, and so, in simulation, we're doing 100 rollouts, okay, that's pretty good. Now 15% change in the detect for simple behavior. Single task is a little bit harder. So you can see even with 50, which is, again, takes a lot of time. And this is all A/B testing, so it takes even more time. You're still, your resolution isn't that good. So what do you do? Okay, now you need to look at cross tasks. And this is where your statistical power actually starts to be useful. You want to understand if you 5% change or 10% change exists, okay, great. You can do it, but now look, so this is weeks of real world evaluation. And that's tough. You can do it if you want to understand how good a particular policy is, but you can't relate across all of the things that you want to care about. And even this hides a little bit of complexity, because actually you need a lot of environmental randomization. You don't want to report against employee distribution, that's misleading. So there's just a lot of time and a lot of engineering that goes into doing this properly so you can mislead yourself. And I don't have Panacea, it's still a hard problem, but there's a few things that we picked up that make this a lot better. So one is that you really want to get the most juice possible from the real world evaluation you do. So A/B testing is completely critical. Always do A/B testing. It feels like it's expensive because potentially you're evaluating the same policy multiple times. But I can basically guarantee if you have sample sizes less than like thousands and the world is not entirely well controlled, you're just measuring the less. The other thing is that we put a little bit of time into building the statistical recipe to do some analysis. So we actually have a sequentially aware test that we use now. So what this does is it actually considers the order of successes and failures. And this gives you more statistical power. So you get more information from a given sample size. And it just really intuitively, imagine that you're planning on doing 20 rollouts of the policy evaluation. If you have 10 failures in a row, that actually gives you a signal which is very different from if you just did the entire run and you have half successes and half failures. And so what you can do here is you can sometimes determine, and you can also do use some of the differences in that sequence of success and failure to get additional information. And there's little stuff. Just think about the posterior, look at things beyond just expectation and other ways to do it. But the other thing that's very important here as well is simulation. And we use simulation really heavily for every policy that we evaluate in the world, probably evaluate 100 or maybe 1,000 checkpoints in simulation. And the idea is really by the time you're doing something for real on a real program, you should have a pretty strong prior about what you expect. And this again just means that you can get a lot more useful throughput from the evaluation that you do. Even though it's actually very resource intensive doing it like this, arguably it is resource rational from the cost-benefit perspective of the team. The other thing that this is really key for is, as you your experiments are getting increasingly complex. So I showed you before our simple setup, which is a fixed manipulation station. This is our mobile robot. You want to be able to have kind of a progression from simple simulation into a real-world platform that's very easy to evaluate on. And then by the time you're putting it on a complicated robot, you're not wasting a lot of time tracking down bugs. And we actually use this to great effect. So we have a partnership with Boston Dynamics. We took the same large computer model approach we're talking about, and we extended it with the Atlas robot. There's some really cool aspects here, like the command and foot placement. So it's doing full body commands directly from the policy, not just the upper body. And incredibly good people on this project. So a big part of the success is due to them. But all of the careful work that we did leading up to it, then by the time we were ready to deploy out this robot, we knew that a lot of the logics already validated out, and we knew what recipes we wanted to use because we already validated them easier, using less complicated settings. One thing that's pretty cool with this robot here too is just you can see how much that fluid mood is changing as the robot moves. So this is actually, so beside this is a pretty cool active sensing model as well, where the commands given to the robot are actually very highly correlated with what the perception system is. Okay, so not a lot of time, so moving fairly fast through these, but the third thing that I want to talk about, and the one that I feel is also incredibly important fundamentally, is avoiding what I might call like deployment black hole. And I'm going to get a little abstract here for a second, but what I mean by that is pretend that this cartoon here is like the distribution of robot data. So you have some really neat paragraph, you collect a lot of data, and this simple 2D cartoon, that's like the data distribution for this company. Alright, so that seems great. You take your robot, you deploy it in the world, you're ready to go, and you notice you have some mode of failure that pops up all the time. I don't know. Maybe this is you're serving lunch. Maybe occasionally people ask for an order that's a little bit out of distribution. Or maybe it's being deployed in a facility that's a little bit different dimensions right now. You're like, okay, the robot did things that didn't make sense there, that's fine. We'll get that data, we'll add it to the data, make sure we're all in places. And then the season changes, and all of a sudden it's winter and it's snowing out and the lighting is different. You have some of the same problems, but it's like, no issue, we patch it, all right, sure. And now all of a sudden the robot changes. You made some hardware upgrade, the robot's a little bit different, and it's like, okay, cool. Now I've got a few more things to patch as well. And some of this is inevitable, it will happen, there's no magic thing that protects you here. But you would really like some hope that you can generalize beyond just the things you found out. And you also like some hope that you're basically great. You won't just immediately be outside of the support of your data and all bets are off. And so in general, this is where pre-training is important, but there isn't that much robot data in existence yet. And so another thing that I think is very important is thinking about ways to build multimodal data distributions. So this is data that isn't just robot actions, in order to broaden the support of the pre-training data and be more graceful in situations like this. And now, when something unusual happens, it might be outside the support of your action and robot data, probably the system won't work as well there, but you aren't totally outside the support of all your data. And the paradigm behind this, which I refer to here, which is clearly the direction the field is going, are these multimodal many-to-many models that really unify a lot of the separate problems in AI. So, these are models now that are predicting things like actions, that are predicting text, but they're also predicting, let's say, images or these robot observations into the future. And I think first, there's just a lot of benefit to have for doing this for data reasons. Second, you can play a lot of games now to test time compute. You can try to supervise based on efficiency. And things like MCTS, reasoning models, a ton of techniques that have been promising in certain areas of AI. There's a clear road towards training newer models as well. So, a lot of reasons why this is good, many different forms that this can take. One that I'm particularly excited about in the near term is actually unifying video prediction with robot action prediction. So this is a work from a very talented intern that we have at Chinook. And this is called Unified World Models, and it's basically unifying action prediction with inverse dynamics with full video prediction. You can, depending on what data you have going through the model, you can condition on some subset of information. So you can have video-only data in the mix, and you can basically pass this video generation. Or if you have robot data, you can actually supervise both on the future of observations, predict actions in the future. Here are two observations, what action went between them. And the work is still early, but we've shown a lot of promise, and we found better data efficiency. We also found just qualitatively, so this is predicting kind of like key checkpoints in the future here. This figure's a little hard to look at, but if you look at the right columns here, you're seeing like a second or two into the future. The model is predicting what visual state it will look like. And again, it's early, but improvement here is really fast. And I think stuff like this that is very much the way the field is headed. And this isn't the only work as well. There's been a bunch of stuff in the last year or two. A few of the bigger ones are Gen 2, 3 Gen. This feels like it's becoming a low-hanging fruit in getting better efficiency out of just all the data that we're getting as well. And there is a cost here. It's generally a compute cost. Most of the data already exists, but with the pre-training allows it to be even more expensive. But in the same way that robot pre-training, I would argue, is rational from the post-training perspective. The robot data here is still relatively expensive compared to other data, so planning these sorts of data is rational from the robot data perspective. If there's an overall party thought, it's really that just, I would consider rationality targets carefully. There's lots of different ways that you can be rational. I don't see it as being an intention in the state of learning, but I do think it's worth thinking, what is the most expensive right now, and how can I be rational with respect to that? That's all I've got.
Thank you, Ben, for that wonderful talk. We have time for a couple of questions.
And I should also say, too, I just have to go on slide, just that you're excited about building general purpose robots. We've got some really great stuff out there. So, rationality aside, yeah, so a lot of this just comes down to the post-training data mixture. So in this case, the demonstrators tend to work the way. And there's some times where that mixture is multimodal, actually. A lot of times it's multimodal. And so you won't always easily be able to do that. Sometimes the robot will just kind of mode switch between a few different modes. Sometimes even if multiple people on it, they have different preferences. And so you'll see a little bit of this mode switching, just depending on exactly which stuff is relative to the robot.
So what are we happening based on the class that has not been demonstrated?
You still really need to be able to support your data. So if you're doing something that fundamentally hasn't been demonstrated, either in your post-training or in your training, it's not going to work. Usually the failure modes that we see there are one of two things. Either you do something that is sort of random, and with pre-training, actually the failure looks different. Usually it looks reasonable, it's just completely wrong. Often you see a robot that's just picking up random objects and moving them around in their space, almost kind of like a hopper. Or you might snap into the mode of just a wrong task. So it may ignore its language steering, or it may ignore the post-training task. And let's say you have some task from a pre-training data set that has sort of similar, similar environment. You might just do that task instead.
Thank you for the great talk. I have one question. Triggers because the figure that you showed about the distribution of pre-training data as a multimodal distribution data here versus actually the post-training phase. Isn't it really high to actually measure the difference if you're outside this?
So the thing that's tricky here is that the data distribution is actually not a super well-defined concept. I mean, conceptually you can imagine what it means, but actually it's in the feature space, whatever that might be implicitly, in the model that you've learned, are you in or out of distribution? And you don't always know. So there's still a little bit of an art. But generally what we found is that if your pre-training mixture is broader, you tend to have more graceful types of failures. And you might say, well, you're clearly outside of the distribution of the action data you have, but if visually you're in distribution, or from video learning, if you're in distribution there, it doesn't guarantee things will work. But in practice, we found that you tend to either fail more gracefully, or performance just delays a little more smoothly.
Maybe one follow-up question on that. Multimodal refers not only to the inputs, to the sensory data, it also refers to the compensation, pre-training phase. Or you want to consider all possible factors that could happen, like in the joints or whatever.
Yes, during pre-training, generally diversity is good. I would reason multimodal here to be mostly different modalities in and different modalities out, but yes, many axes of variation also are important.
Do you think linear classification
so there's actually been a bunch of very exciting work in this direction in the last couple of years, Robot Progress Bar, and a few others. I'm not sure. I do think I tend to like the Q function formulation, so you dynamically predict either your Q function or your cost to go instantaneously. I like that better than predicting just success or failure, but I think we've seen potential for all of these. I think some form of it will almost certainly play a role. We'll see exactly what the best form is going to be. Yeah.
Great talk. I'm just curious about how would you imagine to evaluate the data you collected? Are there some tricks, like some certain kind of data that you figure out you didn't collect later after you train model and test it? And what are the takeaways from it?
Yeah. Okay, so two answers there. One is from the pre-training dataset side, it's really brutal. I wish I had a better answer for you. There's a lot of intuition. It's very hard to put pre-training in experimental relations over, let's say, thousands of data mixtures. So that piece is more of an art than a science. The post-training piece, that is a little bit more tractable. We've done a bit of exploration there. Currently, one of the things that we've had most success with is almost like a weird offline version of Dagger, where you see the failures of the policy, and then actually you very carefully show recovery from those failures. We'll often sometimes take our post-training data, we'll project it into the feature space of the pre-trained model, we'll look at how it clusters, and we'll sometimes do a little bit of cleanup there. Dorsa's been doing a lot of awesome work lately on making some of this automatic, which I think also would probably be an important piece of the puzzle. But I think in general, it's challenging, and I think probably where the field's going to go is more online methods, and especially as robots are now getting out of the lab, they're solving real problems. We're going to, I think, have a much larger space for things that are like shared autonomy or more traditional Dagger approaches, where as the robot is making a mistake, there's the opportunity to give feedback, maybe even take over and show corrective action, and that's really the data that you want, because it's in the distribution you care about. How can you fix behavior in order to get the outcome that you want?
Let's thank Ben one more time.
Okay, excellent. So for the next part of the session, we will have contributed talks. So I'm going to go up to the stage and get that set up. So just give me 1 minute. Sure.
I just wanted to say hello. We were in contact via email. I'm sorry, that was not appropriate. Yeah, I did not fully read the whole story about relational data, relational inference, relational methods. Yeah, we are working in that field, but not precisely well enough. Yeah, so it was all fine. I need to get used to conferences back again. This is my first international conference trip now since Corona. And
Yeah, I'm so glad to see you again.
yeah, but I'm looking forward
Yeah.
to be here and also to see Dr. Song's talk.
Excellent. So let's go ahead and get started for our contributed talks. So this part of the session will have three components. First, we'll have talks by our three best speakers. Then we'll have lightning talks for about 15 minutes. Lastly, we'll have the poster session. So this will start at 2:30 p.m. and we'll go for an hour overlapping with the coffee break. So before we get to the best speaker talks, I do want to provide some recognition for our best papers and best paper finalists. So for our best paper finalists, we have 3 papers here that I just wanted to recognize. So Cayman, causal action influence detection for sample efficient local manipulation. Momo Act, action reasoning models that can reason in space. And model predictive adversarial invitation learning for planning from observations. So congratulations on being best paper finalist. And now we have the announcement for our best papers. So these 3 papers we felt that had very strong support from the reviewers and very strong alignment with the goals of the workshop. So Mini Diffuser, resource rational multitask diffusion policy training. Rambo, RL, augmented model-based whole body control for local manipulation. And Touch Begins where vision ends, generalizable policies for contact-rich manipulation. Congratulations on best paper. So now we will now have our best papers give a short talk. Do we have the presenters for Mini Diffuser? Yes, okay, come on up. And while you're coming up, is the presenters for Rambo and Touch Begins also here? So which one are you?
Rambo.
Okay, you can stay there for now. For Touch Begins, do we have? Okay, that's okay. Come.
Hello everyone. We're here to present Mini Diffuser. It was done by me and my author at UU. The problem we want to solve is the high computational resources required to train a multitask manipulation model. For example, training the correct requires about 128 GPU days, and F3D takes about 80. RVT, which is much more efficient, still needs 100 days. By comparison, our method, which we call is Mini Diffuser, bring that cost down to roughly 100 day, and that's 95% reduction in training time for diffusion-based robotics policies. So how do we achieve that? In image diffusion, the term is a very high dimensional. For example, every pixel in the image is part of the prediction. Each sample is large, and batching is simply stacking many independent images together. However, in action diffusion, the situation is quite different. The action space is low dimensional, maybe just 6 or 7 degrees of freedom. But the conditioning inputs like images, phone calls, or languages are high dimensional. So this creates an asymmetry. Actions are light to process, but the conditions are heavy. So conventional action diffusion training still use a one-to-one staging, one noise action per condition within a batch.
That means the expensive condition runs a different bin for different frequency size, which is very expensive. So we want to avoid repeating the most expensive part of the pipeline, the conditioning encoder, without adding new information. That's the bottleneck we target. What we do is to sharing the same ground truth action and state from the data side and try to give the model multiple noises samples to construct the batches. In this way, we can save most of the conditions processing time while maintaining the equivalent batch size, or having a lot more larger batch when processing same amount of condition totals. Our solution is we call our solution as level 2 mini batching. Instead of sampling one noises action per condition, we sample many. Formally, we sample B state action pairs from the data site, and for each such pair, we generate noisy versions of the noises of the action from the original action theory. This way, each condition is encoded once and then shared across multiple noises actions samples. This simple change reduces training time and memory while providing equivalent size of batches and keeping the diversity of training signal. To make this batch sampling strategy work in the model side, we adapted the diffusion transformer to prevent information leakage between the action samples. Because now, in the same level 1 mini batch, we are processing multiple noise samples. For each level 2 mini batch, where all samples share the same conditions and ground truth action, we slightly adapt the attention mechanism so that the entire mini batch can be processed as a single sequence of tokens. This eliminates the need to stack along the batch set dimension. Due to the low dimension nature of the action tokens, this approach introduces only a negligible computational overhead compared to processing a single sample. The details attention mechanism is that each action sample can attend itself, but not to other action samples. And the conditions don't attend back to the actions. They only do the self-attention. We implement it with mask attention and kernel queries. This way, the network maintains full conditioning access to the conditions, but ensures independence across noisy action samples. Here is how many diffuser compared to existing baselines. Many diffuser achieves about 95% of best baseline performance, but it uses only one A100A, which is 5% of computation and 7% of memory. So we are delivering nearly the same capacity, but at the order of magnitude lower cost. Due to the time limit, we skip this convolution and this word review. So a quick summary here. Our work is two-level batching, and combined with light architecture tricks, cuts training cost by about 10 times while keeping nearly the same performance. But there are still some limitations. Results rely on arrow-band scale setups. Tasks are mostly quasi-static, and the gains are only in training speed, not inference time. And this is still a multitask mode, not yet a generalist. Thank you.
Okay, we have time for a question, and Rambo, do you want to come up and start getting set up? Thank you. Any questions?
happy to present my paper Rambo here. Also thanks to the organizers. It's a very nice workshop. So Rambo stands for RL Augmented Model-Based Whole Body Control for Local Manipulation, and it has been recently accepted around. Everything is open source, so feel free to use it. So reinforcement learning is a very interesting technique that has enabled the lab robots to operate robustly in the real world. So that video is from our lab, and the other one is from my supervisor Ryan's lab. So it works pretty well with position level control. That means that these RL policies, in most of the case, output the joint angle target tracked by a PD controller. But sometimes, if we look at all these videos, we've been thinking about, okay, most of the times it's passively interacting with the static scenes, and even it's interacting with, for example, boxes, it's also a very lightweight box. So there's no actively, it's not actively taking the reaction force into account for those controllers. Let me give you some examples. For example, in these two, a puppy is trying to push a very, let's say, heavy shopping cart, or this gentleman trying to rotate this very heavy cart. So if we look at these motions, why cannot we achieve them on human? There must be something missing, right? So just simply imitating kinematic motions may not seem to be enough in such scenarios. So what do we need? And then we take back and then figure out, okay, we need dynamics, level, reasoning, and control, which means that we are bringing some model-based things back. All right, so the core idea of Rambo is pretty simple. Most of them should have known what, like the Newton order equations of a Lego robot or just manipulators, and then if we know it, we know how to solve the inverse dynamics. For Lego robots, there were a technique called whole body control, and basically it's giving some acceleration level target or joint level target, and then you solve a optimization problem to try to get the joint feed forward. So this is the whole body control, and only with it, it's not enough. That's why we're bringing RL techniques here as well. So RL as a high level, or let's say we call it as a sandwich structure. So basically, RL have control on top of whole body controller, also at the joint level. And in more detail, we can have the RL policy to give a correction feedback to the acceleration target for whole body controller. And it can also give a correction feedback at the joint level. Here we have some like also common techniques. We have predefined contact modes so that we can directly use to optimize the reaction force. We are using a very simplified model, which is single rigid body. For quadruped, probably it's enough. Though we are doing a QB-based reaction force optimization. And we are training this RL policy with the whole body controller in the room in simulation. So all this standard technique combined, that we can achieve something like this. So if you imagine this is not something you can done with only kinematically, so basically you need to let the controller reason that it has to push a downward force to the shopping cart. It's really learning to lean towards and really change the base angles to be able to push forward. And of course, there are some benefits. We are bringing the traditional model-based things back. That means we have some higher precision in some force interactive passes. For example, here we are trying to command the robot to push forward while maintaining there, and doing working with its legs, and also holding a plane as long as it can. So basically to show the end effector tracking is pretty precise, even in these force interacting tasks. And also we are not sacrificing the robustness from RL, so we can achieve very agile behavior working with two legs, even uneven terrains with pushes. These are the standard RL benefit we get from training. So finally, since we are solving the optimization to get the feed-forward torque, and with RO feedback, we can trade off the precise tracking with the compliance. So basically, we are lowering the PD gains for position feedback, and then just use the feed-forward torque, and we can achieve very high behavior performance, safe interaction with the like this. So to conclude, Rambo is a hybrid framework for whole body local manipulation. It reasons explicitly at the dynamics level, at force level, through this model-based optimization, and it achieves both robust and precise performance. And that's it. Thank you so much.
Thanks very much. Is the touch begins? Oh, right. If you want to come up and start getting this out. And we have time for question. Any questions for Brandon?
Is your open board is applied for the other person? So not use it for other person or to make it like
So for now, it's just a unitary quadruped. Potentially, you can plug in and play with other quadruped robots. Humanoids is a bit more complicated because single rigid body may not apply here. Potentially, you can use more complex models like centroidal or full order. Of course, your training will be longer, but should be straightforward.
We're looking for a converter.
begins where bridging ends, generate policies for contact bridging operation. So in real world, a lot of comps such as this USB insertion is difficult for robots because it requires millimeter scale precision. And in real life, we found that a single collision-based behavior cloning policy can be failed into dangerous collisions. For example, in this plug insertion or the car spotting policy. And also in the real life, we want our robot to operate in a random, unstructured world. So in order to retain those kind of precision within all the visual variations, we also take advantage of the important low-level interaction between the objects during the manipulation task. Because the force feedback is kind of consistent when the scene is changing a lot. And we choose to use this Aniskin, which is a cheap, reusable, magnetic-based tactile sensor in our lab to capture the force information. And as you can see, when the scene is changing a lot, the tactile patterns visualized here is actually consistent across different backgrounds. This all motivates us to develop this vital visual tactile local policy that is able to conduct very precise manipulation and all the random environments. The local here means for locality, and we are training our policy in a local region near the object and deploy out with beyond region parts. So the success of vital comes from three parts. First of all, in order to gain visual generalization, we train a DC policy with smooth augmentation to get a robust vision encoder. And then to further increase the robustness, we continue to refine our policy with a residual reinforcement learning, basically any offset to the connection. And lastly, during inference, we directly use an off-the-shelf rich network model to reason in the scene and localize our object to initialize our policy. For the semantic augmentation part, we first of all collect data with the brainstorm background, and then mask and segment all the object we care about, and then we get a visual encoder that is able to neglect all the important features in the scene. With the augmented data, we train a simple DC policy, and our model architecture is based on BubCube, an efficient transformer that is very friendly for multimodal learning. And we use the egocentric view because it captures the fine-grained information, and it's very clear for the policy to use. However, there's an issue. As you can see from the right-hand side of the video, when it's getting close, the vision kind of loses track because the object is blocked by the worker itself. Tactile, on the other hand, is able to capture the force magnitude and the directions during the contact, therefore able to lead the policy to complete the task. And we found that it is able to get a 40% performance boost with tactile modality. So now we have a moderate DC that is able to get 50% success rate with just a few demos. But there's still the accumulated errors of the DC that is going to harm our policy performance. That's the reason why we continue to add an offset residual to the reinforcement learning. And because of our locality setting, with only 45 minutes of online reinforcement learning, we are able to achieve a very amazing success rate in those all difficult tasks. And then lastly, during the inference, we simply use an off-the-shelf mobile model that we give it the RGBD surface and image, and then prompt it with marking our object of interest. The VLM will directly give us a point in the 2D image plane, and then we can reproject and calculate the 3-coordinate robot experiment and directly maneuver our robot arbitrator. And then we can initialize our trained DC plus RL policy. And thank you very much for listening. Here's our website and code. If you're interested, feel free to pursue. Thank you very much.
Thank you. Any questions? Yeah, let's thank all of our best paper talks once more. Okay, so now we'll begin the part of the session for the lightning talks. While I get set up, so we're going to run all of the lightning talks from my laptop. I'd like to invite everyone who has a lightning talk to please come up to the front 2 rows, please. I think it'll make things a lot easier because we want to go through these slides one by one. I will also be timing, so I will give you, off to the side, I'll be timing at a minute and 15 seconds, I'll say something, and then at 1:30 we'll have to move on to the next speaker. So we're going to go in the order of the slides that they were presented in. So if you give me a moment, I can get that set up. Okay, I think we're ready to begin now. So, will adaptive diffusion constrain sampling for bimanual robot manipulation? Are the audience here? Yes. Okay, come on up. You can use the arrows to
Yeah, hello, we are Pella from Team Thompson, and we'll introduce our work, adaptive diffusion constraint sampling for bimanual robot manipulation. And in the robot tasks, sometimes they require the robots to do some collaborative tasks like assembly or like object transfer. And it's very challenging to generate diverse and constraint satisfying and non-model samples for these high-dimensional systems. And to address this, we propose adaptive diffusion framework that can handle the undefined post constraints and also the size-diffuse inequality constraints. And also we propose a compositional window transformer that can impose the energy values of the constraints without manually tuning them. And finally, we propose a two-stage batch-wise sampling strategy, and that can improve the convergence and also improve the precision. And the key figures that we achieved, like micrometer precision levels, and also the efficiency is like we use consecutive to generate 500 batch samples. And so on the top left, our pass involves two arms holding goals and with a pen on the middle, and then you can see the arm can collaboratively sample some characters and help, and also sampling some points inside a pentagram. And also we can sample some points in the rectangle and so finally these samples can be feed to a motion motion.
Okay, next talk will be AMPT, Adaptive Multi-Objective Projection for Balancing Exploration and Skill Diversification.
To address first your claims on clearly our open line to unsupervised objective. And first, maximizing return information to encourage diversity, and second, maximizing state entropy to promote exploration. However, return information driven diversity often induce only specialization by constraining exploration, while state state entropy-driven exploration, like sacrifice, still distinguishable. Distinguishable. This opposing objective will like completing gradient leading to inhibition of the initial like existing approach, typically sample scale randomly during the fine-tuning phase, thereby failing to leverage the diversity acquired during pre-training. So we propose like RPEP, which explicitly address both challenges. Like first, we adapt the gradient conflict to resolve exploration and diverse gradient conflict. And second, we introduce an adaptive skill selector that aligns pre-trained skill to the downstream test. So our method like achieve statistically significant improvement across maze and NURBE benchmark. That's all. Thank you.
Next talk will be Cayman, causal action influence detection for sample efficient manipulation. This is one of our best paper panelists.
Hello, it's me again. I'm going to be talking about Cayman. So Cayman is a hierarchical algorithm that used to train a quadrant to push a box or an object into the target. So there are several facts new about Cayman. One is that we use causal action influence as an incentivizing reward to help the robot to guide through obstacles or guide with interacting with the objects that is on the train. To measure the chi-score effectively, we leverage a combination of kinematic model and the learned residual dynamics so that we can train this standard at a very sub-efficient manner. Surprisingly, without changing the kinematic model, it works with the complex navigation, such as its multi-obstacle scenarios or asymmetric object, such as a shopping cart. So there are more details in how you learn, and also in the poster session we're going to talk about it. I can also present the next one. Learn more with less. So the motivation is still the same. Once we got a new robot, potentially it has a built-in controller, but we don't know how it works. Even though we just want to provide, for example, base velocity and different positions, but if we don't know how it works, potentially it's hard to bring it into simulation and do more interesting stuff. So for example, this black box controller provided by Spot, maybe now the open source, before we didn't have any access to how it works. So how do we efficiently learn the latent logic and dynamics of this controller? We bring SimFSVGD, which is a Bayesian neural network, but we embedded a kinematic functional prior to it. The kinematic functional prior is really simple. It's just position equals to current position plus delta t times velocity. Something like this. But still, we achieve very sample efficient training for the dynamics model, and we use this dynamics model to train neural policy to track, for example, arbitrary trajectories. And this model, when we have new data coming in and when we maps this new data corrects the accuracy of this kinematic model in a very sample efficient manner in this method. That's all. Thanks.
Next paper would be Traced, Transition-Aware Regret Approximation with Code Learnability for Environmental Design.
Hello, also one of the Traced. Our work is about supervised environmental design. It is one of learning algorithm for reinforcement learning. It is the framework with teacher and students, and teacher gives and generates the high learning potential test for the students. The students get the lowest policy. So we are focused on the high learning potential. So what is the high learning potential? Fireworks use that for PBL, positive real or real using motion recognition. But we introduced the ATPL for the error rate approximation and additional lightweight metric for main probability, which is the first transfer. With these two key components, trace scales, the simplifications, and models, we will see protocol design and thanks for listening.
Next paper is Model Predictive Adversarial Imitation Learning for planning from observation, and this is one of our best papers.
Hello everyone, I'm Tyler, and I'm here to talk about some work called Model Predictive Adversarial Imitation Learning, or MPAIL, for planning from observation. So the motivation being that as humans we can imitate usually without access to expert actions, from view demonstrations, so forth. And as we learn, we also build intuition about the world's dynamics, and for robots these dynamics models have similar dynamics. Inverse reinforcement learning can be used for the former, for smart bullets, and model predictive control has been historically really powerful for the latter bullets. MPAIL unifies these two methods with a planner that learns costs via IRL, while improving through interaction and Pali learning. So this is one of our experiments in the paper, in which first there's a single demonstration collected of the vehicle driving around the track. We collect interactions in the sim, and it trains in sim, so it trains the cost of value in sim. And finally, it's returned back to the real world for deployment. So something to highlight here is that the costs are learned entirely using observations from the expert, but we still have full, direct, and steerable access to the agent's optimization landscape. So I don't know if you can see from there, but you can see the MPPI rollouts and what they're costing, so you can see what the agent's kind of thinking. There's a lot more theory, insight, and results from the paper, so please come by the booth here and say hello.
Next talk will be from simulation to reality, data efficient evaluation of causal Bayesian networks.
Thank you very much. So my name is Karen Ramirez, and I'm presenting on behalf of my student who will not care the visa issues. So basically, the background is using Gaussian Bayesian networks requires a lot of information, right? So it's data hungry. And as I mentioned in the morning, we require, for example, 1 million samples from simulation to actually train the model, the graph, and also learn the probability distributions. And then you also need 80,000 samples to actually test the simulator. And then it's not 100% going to be in the reality, right? So we're exploring this reality gap, and we're actually proposing these guidelines and these suggestions to actually create a data set. And we are releasing the guidelines, we're releasing the current data set to actually create like a benchmark. So we believe this is important, and we're inviting the community to actually contribute to this new benchmark.
The next paper is Spark, Selective Progress Aware Resource Querying, but I believe they could not make it. So we'll move on to the next paper. NERF-AUG, Data Augmentation for Robotics with Neural Radiance Units. Might also have to make it, so we'll move on to the next. Learning on the Fly, Rapid Policy Adaptation via Differential Simulation. Three in a row. Maybe, we'll see the fourth one. MoMA Act, action reasoning models that can reason in space. And that was one of our best paper finalists as well. And Robo SSM, scalable in-context imitation learning via state space.
Hi, this is Yongju from KAIST, and I'm going to present the Robo SSM. Can learn how to manipulate from the example and who can improve the performance by getting more examples. To enable this in Robo, we introduce Robo SSM, the scalable in-context imitation learning is state-space models. It enables to Robo to learn how to manipulate from the examples. And we place Robo SSM replace the transformer into state-space models. Specifically Roman, which has less extrapolation capabilities and real-time inference. It makes Robo SSM can execute the unseen task with the large number of demonstrations. Thank you.
Okay, I believe that's it for all of our lightning talks. So let's give everyone a round of applause. Thank you for our so now we'll go ahead and break for the poster session. So the poster session will be held until 3:30 p.m. And then at 3:30 p.m. we'll have Mark Toussaint have a talk, and then we'll have a panel and debate as well at 4 o'clock. So hope to see you soon at 3:30 p.m.